This is the 27th lecture, 21 March 1994, and the topic is more about diodes, including the catastrophic diodes, namely the Zener diodes. In the last lecture, we had commented that a normal diode which is not allowed to go into the breakdown region, a normal diode which is not allowed to go into the breakdown region, that means if we confine our attention to this region, okay, then the equation to the curve, if this is I and this is V, the equation to this curve is represented by Is e to the power q V divided by kt minus 1. This is the characteristic, that this is the equation that describes a characteristic like this. Now it is found that depending on the material, whether it is germanium or silicon, and depending on the current level that is conducted, it is safe to put a factor eta here in the denominator, where the value of eta is equal to 1 for germanium diodes and for silicon at high currents, at high I, all right. At reasonably large currents, silicon and germanium obey this equation with eta equal to 1, whereas eta is equal to 2 for silicon at small currents. The transition region, the transition between small current and large current, is somewhat fuzzy. So unless otherwise specified, we shall assume that eta equal to 1. If it is specified that eta has to be taken equal to 2, then you take it 2, otherwise we shall take it to be equal to 1. We also showed that at room temperature, the equation at room temperature, where capital T is 300 degree Kelvin, at room temperature, the current can be taken as Is e to the power 40 times V minus 1, where obviously eta has been taken to be equal to 1. If eta is taken as equal to 2, then instead of 40 we shall have the figure 20. You must also remember that this holds at room temperature, where the room temperature is assumed to be how much? 27 degrees C Celsius or 300 degree Kelvin. If the temperature is increased or decreased, correspondingly this figure 40 has to be altered. Now as an example of application of this, let's take a very simple example. It is given that a diode under reverse bias, that is V equal to minus 0.7 volt, which means that it is reverse biased. Well, the convention is this: V plus minus, plus on the P side and minus on the N side, and the current flows like this, capital I. It is given that at a reverse bias of minus 0.7, the current obviously shall also be reversed. Current is given as minus 0.01 microampere. You have to predict the current. What is the current when V is equal to minus 1.4, 0 plus 0.35 volt? And in addition, you have to find out voltage, okay, for current voltage when the current is 18 milliampere. Okay, basically it is an interplay of the same equation. However, there are some simplifying features which I wish you to notice. Firstly, at a voltage of minus 0.7, capital I is minus 0.01 microfarad. Now if you substitute in this equation I equal to Is e to the power minus 40, why minus? Because the voltage is negative, minus 40 times 0.7 minus 1, you see this becomes e to the power minus 28, and e to the minus 28 can be ignored, and therefore this is approximately equal to minus Is, and which means that this current 0.01 microampere is the value of the reverse saturation current, and therefore our equation becomes capital I equal to 10 to the minus 8, 0.01 microampere is 10 to the minus 8 e to the power 40 V minus 1 and you have been asked to find out the current at V equal to minus 1.4. Well, obviously e to the 40 V can be ignored, and I would be equal to minus 10 to the minus 8 amperes. Alright, is that okay? This is double of 0.7, even at 0.7 you ignored it, therefore at 1.4 it would be e to the minus 56, alright, so that can be ignored. If V equal to 0, then obviously the current shall be equal to 0, and if V equal to 0.35 volt, the current shall be equal to 10 to the minus 8, 0.35 times 40 is how much? 14, and therefore e to the power 14, and that 1 can be ignored, alright, and this my calculation shows it's about 12 milliamperes if I am not mistaken. The last part of the question asks what is the voltage if capital I is 18 milliampere, alright. We go back to the equation, that is capital I equal to Is e to the power 40 V minus 1. We have to find out V if I is given, and the simplifying feature is you divide by Is, add unity, take log ln and divide by 40. This will be V, and in most cases I by Is would be very large compared to unity. If it is forward biased, then capital I shall be of the order of milliamperes. For example, here it is 18 milliampere and Is is 0.01 microampere, and therefore this quantity is very large compared to 1, and that can be ignored, and therefore this would be equal to 1 by 40 log of 18 times how much? 10 raised to the 5. Okay, so many volts. All right, now let's look at what happens to this characteristic, to the diode characteristic, when the reverse voltage is increased. This is my current and this is my voltage, and the characteristic is like this. It becomes almost constant, and then suddenly at some point on the reverse voltage, the current starts increasing drastically as the voltage is increased. A very small increase in reverse voltage causes a very large increase in current, and this is called the onset of breakdown. That is, it is as if the diode cannot resist any further, it breaks down. Resist, what does it resist? It resists the flow of current. Now, why does this happen? Basically, there are two phenomena that lead to this. One of them is, you know that under reverse bias there is a separation of charges. On the P side we shall have negative charges, and on the N side we shall have positive charges. So there is separation of charges, and these are uncovered charges, that is, the mobile electrons and holes have crossed the junction. The mobile holes from the P type near the junction have crossed to the N region. The mobile electrons near the junction in the N type region have crossed to the left hand side. Now, under reverse bias, this separation increases, alright. The potential barrier increases. As a result, the electric field E, which is directed from the positive charge to the negative charge, increases. And if the electric field is so large Electric field large means what? Any charge shall acquire an energy of field multiplied by charge is the force. What is the energy? Charge multiplied by potential difference. Okay, an electric field can be caused only by a difference of potential. So the potential barrier increases, and therefore charge multiplied by potential barrier, that energy also increases. All right. Now, if this electric field is so large that it can attract an electron from a covalent bond, there is a silicon atom far removed from the junction, but if the field is so large that it can attract one of the electrons of this covalent bond, that is, if it can cause a rupture of the covalent bond and make electrons free, set electrons free, then as soon as an electron is set free, a hole also is generated. Therefore, what it causes is a electron hole pair generation. All right, and therefore the number of carriers available, that increases. All right, and this onset is distinct. It's marked by a certain voltage. Beyond this, the electric field is sufficient to generate carriers as a result of its ability to draw electrons from a covalent bond. After all, a covalent bond also has a certain amount of binding force. If the attracting force cancels this, then the electron gets free and carriers are generated. And this kind of a breakdown, or this kind of an increase in current due to an increase of reverse potential, is the so-called Zener breakdown, Zener, and occurs in a junction in which both sides are relatively heavily doped. In other words, the number of impurity atoms on both sides are relatively large. Heavily doped junction, Zener breakdown occurs, and the Zener breakdown voltage V sub B, the voltage, reverse voltage at which the Zener breakdown occurs, can be very precisely controlled by controlling doping. That is, the larger the doping is, the smaller is the Zener voltage. It can be precisely controlled, and you can make a Zener diode with almost any breakdown voltage, so long as, one point must be remembered, so long as, you see, as soon as a breakdown occurs, the current increases drastically. Current multiplied by voltage is the power dissipation. So long as the diode does not burn out, if the power dissipation, if the power is within the dissipative capability of the diode, then the process is reversible. In other words, as soon as you remove the reverse voltage, the diode comes back to its original shape, and you can again make it break down, you can again bring it back to normal operation. These are all reversible operations, and a Zener diode, as it is called, a diode, relatively heavily doped junction diode, which is operated in the breakdown region, is called a Zener operation or Zener diode. A Zener diode can also be used as an ordinary diode. All right, in the forward direction, if you bias it in the forward direction, it can be used as an ordinary diode. All right. On the other hand, suppose the doping is light, but doping is heavy means that the electric field has ready access to covalent bonds which it can rupture. Doping is light means it does not have ready access, and therefore in a junction in which the two sides are relatively lightly doped, Zener breakdown may not occur. But before Zener breakdown can occur, that is before, not before, yeah, okay, even before, theoretically, the possibility of Zener breakdown sets in, the carriers, the minority carriers, for example, what are the minority carriers in the n-type region? Holes. thermally generated holes, all right. These travel from the right side to the left side, and if the reverse voltage is high, then it might acquire enough energy to set an electron free by colliding with a neutral atom, all right. There is a neutral silicon atom here, and this hole collides with this. If there is a collision, there is a sharing of energy, and if this hole shares some of its energy to the silicon atom, it might give at 1.1 electron volt to an electron, and it might set free, all right. So this basically occurs due to collision, whereas in the Zener region there is no collision. It is the Zener breakdown is a field effect, whereas the one that we are talking of occurs due to collision of high energy particles with neutral atoms, all right. Now suppose a high energy charge carrier collides with a fixed atom and sets one carrier free. This carrier, the carrier that is set free, in turn accelerates in the field and can set other electrons free from other atoms, and this sort of builds up. This sets, let us say, 2 electrons, then this goes and this sets more electrons, all right, and it's a kind of an avalanche effect, and this kind of a breakdown which occurs due to collision of carriers with fixed atoms is called avalanche breakdown. The only thing that is to be remembered is that Zener breakdown occurs due to electric field in a material in which there is relatively heavy doping. Avalanche breakdown occurs due to actual collisions of high energy particles with fixed atoms, and can occur even in lightly doped junctions, all right. In practice, when a breakdown occurs in a diode, it is usually a combination of both, that is the electric field and also high energy particles, they come into effect. However, as I said, the Zener effect is more popular because it can be precisely controlled. Avalanche breakdown is not as precisely controllable as Zener breakdown, and therefore Zener diodes are very popular in situations where you wish to keep voltage across a load constant irrespective of the current drawn by it. If you look at this, the ideal characteristic would be if this curve falls sharply vertically down, then you see the voltage remains the same, but the current can increase depending on, current can increase or decrease depending on what you want, what the load wants. The capability of a Zener to maintain a constant voltage irrespective of the current, constant voltage irrespective of the current, what is it in terms of circuit theoretic terms? It's a voltage source, not current source. It's a voltage source, keeps its voltage constant irrespective of the current, and therefore the Zener can be used as a voltage source, which means that you can stabilize voltage across a load. And in that situation, a Zener diode is the circuit that uses a Zener diode to make such constant voltage across a load is called, this circuit is called a Zener regulator. We shall look into the Zener regulator in a moment, but let us systematically proceed to find circuit equivalence, electrical circuit equivalence of the normal diode and the Zener diode. Then we shall see how it is applied. A normal diode, you see, we can always work, of course, in terms of I beg your pardon, this is not correct. A normal diode has a characteristic like this. It rises sharply like this, then it goes below and falls sharply like this. There is no kink here, it's a continuous curve, all right. Now we can of course work in terms of the in terms of the current voltage relation, that is I equal to Is e to the power 40 V minus 1. But this, as you see, is a nonlinear relationship, alright, and analysis every time by invoking this equation becomes a difficult job. So electronics engineers prefer to have a model, and that too a linear circuit model, alright. So what one does is, one of the most ideal things that one does is, one assumes that the diode characteristic, this Is is a very small quantity. So for an ideal diode it should have been 0. For an ideal diode, as soon as the voltage is positive it should conduct. So this green characteristic is that of an ideal diode. An ideal diode is like an ideal switch, it is either on or off. When a switch is on, it can conduct any amount of current with a voltage drop of 0. That is what is represented by the green curve, alright. So an ideal diode is like a switch. When it is off, the current is 0. Any voltage drop can occur, but the current is 0. You can connect any voltage source between these two, but no current. When it is on, the switch is on, any current can be conducted with 0 voltage across it, alright. This is the ideal situation. Now one of the ways that a non-ideal situation can be taken into account is to approximate this by means of a straight line, a vertical line here, alright. So we say it is 0, the current is 0 up to this and then goes up like this. We have introduced one non-idealness, namely we have said that the diode does not conduct exactly at 0, it conducts at some voltage here. Mind you, we are approximating this red curve by the blue curve, and this voltage is called the threshold voltage, VTH, and is of the order of 0.7 for silicon and 0.3 for germanium. Now this curve can be approximated by an ideal diode. Now we shall use the symbol I inside to denote that it is ideal, alright. An ideal diode, that is a switch, but this diode does not conduct till this potential rises to 0.7 volts. So we have a battery which is equal to the threshold voltage. So this is the symbol, this is the model for the non-ideal diode, non-idealness being only in terms of a threshold voltage, alright. This diode in the reverse direction, this model, if the voltage here polarity is reversed, it does not conduct, alright. This diode conducts only when V exceeds VTH, and once V exceeds VTH, the diode acts as a short, alright. Now what happens in the reverse direction? This diode does not conduct in the reverse direction, isn't that right? If the polarity of V is reversed, there is no current flow. Now to account for the current flow in the reverse direction, that is the reverse saturation current, we can, if we so desire, modify this to include a current source here whose value is equal to Is, alright. This accounts for a practical diode. This is a good model for a practical diode when the diode is still thought of as a switch, alright, in the forward direction. In the forward direction it is a switch, in the reverse direction the current is a constant. This current is almost a constant, alright. Now let us complicate it further. Let us make a more practical model and for a more practical model, let us draw the characteristic negative, and then we are confining our attention before the breakdown, before breakdown occurs, alright. And what we do now is that we represent this part of the curve by means of a straight line, alright, the rising part. It is not completely vertical. The rising part we make it, we we approximate it by means of a tangent, a straight line, all right, which is inclined at an angle slightly less than 90. If it was 90, then our previous model would have been valid. Now obviously the resistance of this, the resistance corresponding to this is current, this is voltage. The resistance corresponding to this, what is the resistance? Delta V, delta I. In the previous model, when it was vertical, the resistance was 0, and therefore all that we have to do now is to take an ideal diode I, then the threshold voltage VTH, which is 0.7 for silicon, and we shall have to use a small resistance, we call this RD. The D stands for dynamic, that is, it is the slope of this line, all right. And then if you want the reverse saturation current also to be taken into account, well, you connect a current source, and this is the linear equivalent circuit of a diode. And most of our practical diode circuits can be analyzed in terms of this equivalent circuit. On the other hand, if we take well, before we take a Zener, let me take one or two examples. Suppose you have a 60 volt source, a silicon diode. A silicon diode means the threshold is 0.7, and then you have a 15K resistance, all right. We want to find out the current in this circuit. Obviously the current in this circuit shall be, if you replace this by its equivalent circuit model, it is a forward bias diode, forward bias 60 volt plus minus, and therefore IS shall have very little effect, all right. So you can ignore IS. If you also ignore RD, the dynamic resistance of the diode, well, if you want you can include it. Obviously the current in this circuit shall be 60 minus V threshold, that is 0.7 divided by 15K plus RD. Usually RD is of the order of a few tenths of ohms, and therefore this can be ignored, and the current becomes 59.3 divided by 15 milliampere, all right. And this, yeah. If you are not ignoring IS, all right, then you apply superposition. That is, first you find out due to 60 volt, then you find out due to IS. IS is now a current source. So you have a circuit in which both current and voltage sources are there, and you have to solve it exactly. For example, if I have a reverse connection, let's say I have a 6 volt, then a 1K, then a diode connected in the other direction. This would serve as a good example. If I have a diode like this, then obviously this diode is reverse biased, and in reverse bias you can ignore the ideal diode, the threshold voltage, and the dynamic resistance. So all that you have to do is to replace this by means of IS. Now will it go down or up? It will go down. It is the reverse saturation current, and therefore what you have now is a 6 volt, 1K, 5K and IS, and you have to find out the current through the load, this I. Obviously you can replace this by a Norton source, then you have 6 ampere, actually it will be 6 minus IS, all right, 6 ampere current source, and then another current source IS in parallel with 1K and 5K. So this current can now be obtained by current division, all right. 6 minus or 6 plus? 6 minus, because the equivalent source of this is 6 ampere 1K, that's it. This current goes down, so 6 minus IS. 6 milliamperes. Yes, that is correct. 6 milliampere minus Is. Is is of the order of micro, and therefore the current shall be controlled by basically by 6 milliampere, and you can show that this would be, how much would this be? 1 milliampere. Okay. So if we are given a diode model, or if we are given a diode characteristic, we can find out a model and analyze circuits in terms of the model, rather than using capital I equal to Is e to the 40b, because taking logarithm, anti-logarithm, and in a nonlinear circuit you never know, you never are very sure of what you are doing. Now let us look at a Zener diode. A Zener diode, as I said, can be worked as a normal diode in the forward biasing condition. That is, in the forward biased condition, well, you can represent it by a switch if you so desire, switch with a threshold if you so desire, switch with a threshold and a dynamic resistance, switch with a threshold, a dynamic resistance and a reverse saturation current. All this applies under normal conditions. A Zener diode is not operated under normal conditions. That is not its purpose. A Zener diode is operated in the reverse biasing condition, and one of the models that one uses is this, that is, one approximates this by means of zero current. Is is put equal to 0, and then a vertical line like this. I must tell you that the actual characteristic is like this, not a vertical line. This is the actual characteristic. It has a slope. It has a finite slope. All right. Now, how do you represent the Zener diode? All right. What circuit model do you use for the Zener diode? Well, if I use the red approximation, red characteristic, then obviously all that I have to do is that there would be a threshold voltage. All right, and this is good enough. We have an ideal diode in conjunction with a threshold voltage, which obviously is the breakdown voltage, the voltage at which breakdown occurs. All right, and you see that if you apply a reverse bias here, then the diode shall conduct. If you apply a bias like this, if you apply a voltage like this, the diode conducts only when V exceeds VB. All right, and after that, if it is the red curve, then we have approximated by an ideal diode. All right. Now, in this, if you want to include its behavior as a normal diode, obviously you should put a ideal diode here, or an ideal diode in conjunction with the threshold voltage, RD, reverse saturation and all that. All right. Now, since we are not using a Zener diode in the normal operation, we can forget about this. Is that clear? We are only considering the equivalent circuit when it is biased, when it is used in the Zener region or the Zener mode of operation. Now, once again, the sloping character of the actual Zener diode can be approximated by including a resistance, and therefore what we do is, I should use some other color, let us use yellow. What we do is we approximate up to this, all right, the yellow line, and then we approximate by a straight line whose angle with this axis is slightly less than 90, and you can define a dynamic resistance for this characteristic, and all that you have to do is to include a resistance here. Include a resistance here, you call this RZ, the dynamic resistance of the Zener diode. All right. Can you see this? Can you see the yellow color? No. All right. This is RZ, and this is a fairly good representation of a Zener diode. VB, as I said, can be controlled. You can get Zener diodes right from let us say 6 or 7 volts to 100 volts by controlling the doping. The resistance, this resistance is of the order of 100 ohms, alright. And to illustrate the application of a of the Zener diode, the most important application, namely a Zener voltage regulator, we take an example. Well, the motivation is this, that if you want a DC power supply, what you do is you take an AC, you transform it step up or step down, subject it to rectification, half wave, full wave, bridge or the other type. Then you use, to kill the ripples, you use filter, you smooth out, and the output should be pure DC, alright. This is VDC, and then you apply to the load, let us say RL. Now obviously this VDC is not an ideal voltage source. Why? Because looking back, the Thevenin equivalent resistance is not 0. The filter has series inductors which have resistance. The rectifier has diodes which have resistance, dynamic resistance. The transformer has resistance, and therefore this VDC that you see can be used as a voltage source and a resistance RS, a source resistance RS, and then an RL. Now if VAC changes, if the line voltage fluctuates, which is a very common and unpopular phenomenon in Delhi and the rest of India, the line fluctuates from anywhere between 190 to 400 volts, then obviously VDC shall also change. VAC shall cause a change in VDC. That is one thing. Second thing is, if the load fluctuates, you want the fan to be at half speed or full speed, you want to control the lights, alright, then RL fluctuates. If RL fluctuates, then the current drawn by the load fluctuates, and therefore the voltage drop in RS also fluctuates, which means that the load voltage fluctuates, alright. To counter both of these, we use a Zener, alright, and the circuit is like this, very simple circuit. What we do is, the VDC source, we call this V1 plus minus, this may represent the source resistance or a resistance connected intentionally. One has to connect a resistance here, and then you have the Zener. The Zener is represented like this. It is represented by means of a wavy line here instead of a straight line. If it is a straight line, then it is a normal diode. If it is a wavy line like this, then it is a Zener diode, and you see the Zener is connected in the reverse biased mode, and then you have the load RL, alright. This is the circuit, and it is this voltage which is required to be maintained constant. Now you see the equivalent circuit of this RS, then the Zener you shall represent by, because it is operated in the reverse direction, all that you need to include is an R sub Z and the breakdown voltage. In which polarity? Plus up or minus up? No. This is VZ, let us say, the Zener voltage, the breakdown voltage. Instead of VB, we say it is VZ, and then you have the load RL. Oh, the diode obviously conducts, isn't that right? Otherwise current cannot flow. That is an ideal diode, so it represents a zero resistance, short circuit. So you have not introduced the diode. If you so desire, you include a diode, alright. Now this is VL. Now we can analyze this circuit by KCL. That is, what we have is V1 minus VL divided by RS. This is the current coming in, shall be equal to VL minus VZ divided by RZ. this is the current through the Zener resistance, Zener diode, plus the current going through the load IL, which is equal to VL divided by RL. Alright, very simple analysis, but very significant improvement in the characteristic. Can I remove this? Have you written down this equation? If I simplify the equation, now I can find out VL in terms of V1 and Vz, and the relation, I will skip the algebra, the relation I have worked out to be V1 divided by Rs plus Vz divided by Rz divided by 1 over Rs plus 1 over RL plus 1 over Rz. Simple algebra, you can show. To get an idea, let us take some typical values. Let us say Rs is 10k, 10 to the 4. Let us say RL is 20k, that is 2 times 10 to the 4. And let us say Vz, the load voltage I want to maintain constant at, let us say 10 volts. Vz is 10 volts. And typical Rz, the dynamic resistance of the Zener diode, is 200 ohms. Then you can show that VL, if you substitute these values, you can show that VL is 1000, again I skipped the arithmetic, 1000 plus twice V1 divided by 103. Alright. Now Vz is 10 volt. Now V1, unless 2 V1 is comparable to 1000, obviously VL shall remain a constant at 1000 divided by 103, which is slightly less than 10 volts. Alright. For example, suppose V1 is 16 volt. This gives you VL equal to, I have calculated this, to 10.02 volt. If V1 now increases, the DC voltage increases by 50%, which means that V1 equal to 24 volt. From 16 to 24 is a 50% increase. The VL changes only to 10.17. You see how constant it remains? For a violent fluctuation here from 16 to 24, the load voltage changes only from 10.02 to 10.17, and delta VL, if you calculate this, 0.15, oh, it's simply how much? 1.5%. That's it. 50% fluctuation in the DC is reduced to only 1.5% fluctuation in the voltage across the load. And this is the most common method of voltage regulation, the simplest and the most common method, used in instrumentation, used in all kinds of applications. Unfortunately, very high voltage Zeners are not available. Very high voltage Zeners are not available, and therefore this kind of regulation is limited to low voltage only. Next time, tomorrow, we will start transistors.